Welcome to the CERIAS seminar for November 18th, 2009. It's my pleasure to introduce Professor Jerome Miklau, who joins us from the University of Massachusetts. Dr. Miklau, 4 years back, obtained his PhD from the University of Washington, working with Dan Suciu, and actually at one point was working on a joint project with some of us here at Purdue. Among other things, Professor Miklau has the distinction of being the first winner of the ACM Sigma Dissertation Award. So we're very honored to have him here with us, and we'll hear about his new work going on in analyzing private network data.
Thanks, Chris. Hi, it's good to be here. My name is Jerome Miklau. As Chris mentioned, I'm presenting joint work with our graduate students Michael Hay and Chao Li, and some faculty collaborators at UMass Amherst, David Jensen and Don Towsley. We also collaborated with the University of Washington on parts of this work. Vibha Rastogi and Dan Suciu are our collaborators there. Please stop me at any time to ask questions. Don't be shy about that. So this talk is about social networks, technological networks, any data that looks like a graph. So I like to start out with some concrete examples of social network data. The graph that you see here is a very famous social network. It's commonly called Zachary's Karate Club. If you've read the social network literature at all, you may have encountered this graph. It was data collected by a sociologist named Zachary, who went around to every member of the karate club and asked each member who they were friends with and drew this graph to study the formation of communities and how community formation evolved over time. So it's a rather small social network, but an important one that people are still using as a kind of base case for algorithms that they study. This is another social network, one that's a little more sensitive since privacy is the focus of this talk. This is a social graph based on romantic connections amongst high school students. This is part of another sociological study where I believe they were studying the structural patterns that evolved in such a social network. They were observing things like there's one big central ring that you see here, but other than that, there's a lot of tree structures in the graph. Here's another example of a highly sensitive network data set. It's a community of drug users and sexual partners in Colorado Springs. This graph was used to study disease transmission, the transmission of HIV in a community, which is highly determined by the topology of the graph. Okay. This is a recent data set very recent data set that was collected by monitoring mobile phone users and inferring links based on the location of users and their communication over mobile phones, and they were comparing that with self-reported friendship links to understand whether people accurately report friendship and how it corresponds to who they actually come into contact with. So those are all examples of social network data. Some of aspects of the data is more sensitive than others. Those are all relatively small graphs that I can make pictures of for a talk like this. But these days, people are also collecting truly massive graphs. So this was a World Wide Web conference paper from 2008, which studied instant messaging traffic through Microsoft Messenger, I believe, was the platform. And this network consisted of 180 million nodes over 1 billion edges. Okay, so we can't even visualize this network. It's too large, but we can study its properties, and this paper looked at a number of properties there. So we'd like our privacy mechanisms to be able to scale to the massive graphs that are collected these days. So coming back to the issues of privacy, each of the graphs I showed you may be more or less sensitive, and I'll talk in a moment about what is sensitive in a social network. But let me just point out here that privacy is a major obstacle to the dissemination of this data. Getting this data to the people who need to analyze it is a hard problem, and it's often an obstacle. So one of the things that may happen is that analysts just can't get the data that they want. The data is collected and it's stored somewhere, but the analysts aren't able to study it. If that doesn't happen, we may be able to work out limited availability. So within the institutions that own the data, some people analyze it, but or they may make some limited agreements with certain people who get to study it, or we may have availability, so data is available, but at some cost. So the cost might be a privacy cost to the participants in the data set. An example is a very common data set is the Enron email corpus. So email data sets are hard to come by because people care a lot about the privacy of their email transmissions to other people, but analysts would like to study real email data sets. So one of the few data sets that is publicly available is only available because Enron got sued and the lawyers posted on their website transcripts of subpoenaed email. So the cost to privacy of the managers at Enron was severe. There were a lot of sensitive information in that data set. Maybe you don't care because they were managers of Enron and they violated the law, but still, sometimes we get important data sets only as a result of violating people's privacy. In other cases, we have data sets, for example, crawls of online social networks, but they are biased because operators of online social networks don't really want us to crawl their data sets, and so there are some mechanisms that prevent us from crawling them accurately, and that introduces bias. So getting data to analysts is hard. And the overarching goal of our work in this area has been to understand the extent to which we can permit accurate analysis of graph structured data without violating sensitive information about participants. So to date, we have focused on topological properties, means the structure of the graph, and not so much on attributes that may appear on nodes or on edges in the graph. So I'm going to talk today about two specific tasks that we've studied. The first is the degree distribution of a graph. I'll describe these later. And the other is motif analysis. But other things that we would want to study on a network topology would be the community structure, how communities form in the graph, where the communities are, simulate processes on networks like routing, search, the spread of rumors or infection, and the resiliency of networks. And we're moving towards those analyses now. So in the remainder of the talk, what I want to do is paint a little bit of a high-level picture of what people are doing, because this problem is getting attention in the literature over the past 3 or 4 years. What people are doing in terms of protecting network data. Then I'm going to present our work on specific tasks, and it's going to use a notion of privacy called differential privacy. Some of you have probably heard of it, but many of you may not have, and so I'm going to review that in some detail. And then I'll present the main technical chunk of the talk is on the estimation of degree distribution. Then I'll quickly go through some details about motif analysis and wrap up. Again, please stop me at any time if you have questions. So here's a toy example of a graph, and we see that there's a node table. The node table is kind of the classical form of data that we've thought about protecting before. So each entity is a row in that table, and maybe some of the properties of those entities are sensitive, and we would want to safely publish aggregate properties of that population without revealing one particular row. Now, when we have a graph, we also have an edge table, and the edges are also sensitive information. So an identified edge in a social network may be a sensitive fact that we need to protect. The fact that Alice talked to Bob can be sensitive in some of the networks I showed you earlier in the talk. There are also implied properties of the graph. For example, the degree of an individual could be sensitive. In a collaboration network, you might want to advertise your high degree. In a romantic network, you may want to advertise your low degree or hide your high degree. In addition, implied properties that are implied by the connections in the graph can be sensitive. For example, you may want to hide the fact that most of your friends are Democrats. Okay, or that most of your friends are over age 50. Okay, properties like that can also be sensitive. So what is sensitive in the data set that represents a graph is more complicated than tabular data that is common to the census or some classical settings. It's part of the challenge that we face in protecting this data. So one of the first things that we try is when we try to protect, and people often think of this, when you try to protect a network, is what we call naive anonymization. So on one side, on the left side of the slides, you see the original network, and there's letters on those nodes. They're pretty small, so you may not be able to see them, but they're meant to represent names. Okay, so the original network has some names, And naive anonymization basically strips the names off the graph and releases the graph on the right, which has maybe random numbers in place of the names. So this naively anonymized graph is essentially an isomorphic copy of the graph. So it's perfect for studying topological properties of the graph. I could measure path length distributions, and I could simulate processes on this network, and there would be no loss of information there. Unfortunately, this type of anonymization is not secure. So the problems that can result from naive anonymization is that one problem is that the adversary can have some external information. So I may know that Bob is a member of this community, so he's in that graph somewhere, although he's not identified. But I can look using the information I have about him and try to find matching nodes. There might be one matching node, or if I know a little bit less about Alice, or Alice, the information I know about Alice is less distinguishing, I may have multiple candidates for Alice, but I may be able to narrow those candidates down. Now, if I re-identified Bob and I re-identified Alice in the naively anonymized graph, then I could just inspect the graph and see whether there is an edge between them, and I would have disclosed an identified edge, which may be a sensitive fact. Okay, so we did some empirical measurements when we first started working in this area. We spent a while trying to understand the extent to which the structure of an individual in a graph, particularly the local structure around an individual, acts as an identifier. How unique is your structure in a population? And if I knew a little bit about your structure, how successful would I be in finding you in that naively anonymized graph? I won't go over this in a lot of detail, but the bar chart is representing the success in re-identifying the population. The H1 along the bottom there is essentially meant to represent a degree signature, and the H1 signature is just the node's degree. So if I knew degree of each person in the graph, how many people look unique with respect to degree? The red part indicates uniquely identified individuals, and it's almost no one. So almost no one has a unique degree in the Friendster network, which is quite a large network. But if I go to H2, which is not only an individual's degree, but their neighbors' degrees, then I have more information about each individual. And that information is highly distinguishing. In fact, about half of the individuals in the Friendster network are uniquely identified by a kind of signature which reports their degree and their neighbor's degree. So that I've gone one step out, and I can go further steps out by refining these signatures, neighbors' degrees, and so forth, and I get more specific information. Okay, so that's some empirical evidence that suggests that structure is highly identifying in networks and is going to lead to attacks on naive anonymization. There are other attacks that have been proposed in the literature, and I'll mention them quickly because they're interesting attacks. In the World Wide Web Conference in 2007, Backstrom proposed an active attack. An active attack, question? Yes. Half of them are uniquely identified. The other half may only be identified, you can sort of identify more than one possible match for those individuals. And those colors, I didn't explain this that carefully, but those colors are representing the size of the set of candidates that you get when you try to match that individual. So the yellow is a portion of the population that ends up being identified to within 5 or 10 candidates. Does that answer your question?
Yeah, so the background you have for this bar is accurate background, or like it could be some error, like because in this such a big network,
Yeah.
It's not like if you a node has 12 degree.
Yeah.
It's not likely you just know you have 12 degree. Maybe you know that the degree is around maybe 9 to 15.
Yeah, that's a very good point. So the speaker is pointing out, the question is pointing out that our information may not be precise. I mean, oftentimes the background information that you have could have some errors in it. So if I go back to, did I skip over this? In this example, you may ask, what do I mean by saying that Bob has 8 neighbors? Do I mean Bob has exactly 8 neighbors and no other neighbors? Or do I mean that I know that Bob has these 8 neighbors and there may be more neighbors? That's an example of having some approximate knowledge. And we studied that, and I'm not presenting that in this talk, the results, but we did look at the difference between the success in identifying people, and it does have an impact. So you will be less successful with approximate knowledge, and it's a good point. Okay, so I wanted to mention this active attack. So an active attack is an attack in which the attacker can inject information into the data set before it's anonymized. So think of an online social network in which you can create new identities, and you can even create edges between identities. And the attacker will therefore modify the graph, and then it will be naively anonymized, and then the attacker will do some inference on the resulting graph. So what they proposed was an attack in which they create a small set of identities, the blue nodes, and they wire them randomly together. They just create a small random graph there in the data set, and then they choose 2 targets, the orange nodes, and the goal of the attack is to identify whether those 2 nodes are connected. And so they wire that funny subgraph, the blue subgraph, to those 2 orange nodes. Then the anonymization takes place. So they strip all the names off and they publish this isomorphic copy. And then the attacker's challenge is to find the blue subgraph in the graph. And then using that subgraph, they just go to the orange nodes and inspect whether they're connected. So what they showed in that paper was that the blue graph can be actually very small. You don't need a lot of blue nodes. If you just wire them together randomly, with high probability you will be able to find that blue subgraph in the much larger graph. And furthermore, there's some subtleties like you'd like to be able to do that and not get detected by anyone who's trying to stop you. So you can look at that paper. Another more recent paper was a kind of global attack in which one big network, I think it was a network derived from Twitter, was assumed naively anonymized, and then the background knowledge that was used was a network derived from Flickr, a different social network with some overlap in the participation. And that was assumed to be an identified network, and then they try to run an attack where they kind of do an overlay of the 2 networks to re-identify individuals. Okay, so I'm just going over those briefly to give you some idea of the subtleties of what can happen. So, naive anonymization, the big picture point is naive anonymization has a lot of flaws, and it's not a safe method for protecting networks. So people have been trying to do better things. One theme of the work has been to create similarity in the structure of the nodes in the network. So that Sigmod 08 paper tried to bin degrees and make every different degree that occurs in the graph have at least k other people that share that degree. And it provided some resistance to an attacker who has degree-based knowledge. Other people have tried randomizing edges in the graph. Okay? Other people, including us actually, have tried clustering the nodes in a graph and then reporting statistics about those clusters, then allowing an analyst to sample from that graph-like object and analyze the samples. So actually a few other authors have also considered clustering and summarization methods. So I'm not going to talk about those techniques in detail. They're all instances of what I call data publishing. So we've got the original network on one side of the line, and we publish a graph or a graph-like object that's distorted in some way for privacy. Okay, so that has some good points and some bad points. So from the standpoint of ease of use, it's good because the analysts want a graph to hold on to. They don't want to just run a one-time query, really. They want to do knowledge discovery on the graph, or they want to refine their algorithms as they study the graph. So it's nice if they can have a graph to hold on to. Unfortunately, these data publishing techniques, most of them have relatively weak privacy guarantees, and it's quite difficult to make formal statements about the impact of the anonymization on the accuracy of specific tasks that you want to carry out. Also, the scalability is sometimes bad, especially with clustering large graphs is computationally hard to do. So what I'm going to talk about today is a shift in techniques that we've done since our VLDB-08 paper. We've been looking at output perturbation techniques, where instead of publishing a graph, you, as the data owner, receive queries and respond to queries with noisy answers. This has some limitations. For example, with ease of use is not so good, because as I said, it's difficult to decompose a data mining task into a set of small set of queries, and we'll come back to that. But the advantage is that we can have very formal privacy guarantees and very and precise bounds on the accuracy, and the scalability is quite good because all we have to do is compute the query answer and add some random noise. Okay, so let me go into some more detail about output perturbation as a technique. We're going to use output perturbation techniques that are designed to satisfy a notion of privacy called differential privacy. This has been in the literature for a few years now, but there are comparatively few results for analyses involving graphs. So the basic idea, as I said, is you compute the true answer and you add random noise. So I'm going to go into some more detail about differential privacy. Does anybody have any questions at this point? Yes?
I was a little puzzled by the ways you were trying to protect information, including randomized pages.
Yeah.
You started with a graph. It looks like you ended up with an entirely different graph. If there is no way of going back, then what analysis does it do when the new graph is going to be happening to the original one?
Well, that's something that is typically in these works measured empirically. So we would apply anonymization on a data set, and then we'd try to do a bunch of analyses. Like we could run a disease transmission study on the original graph, and we could run a disease transmission sort of simulation on the anonymized graph and look at the difference between the findings that we would derive. And there will be a difference, and that difference is the information loss as a consequence of the privacy, and it may depend on the privacy parameters and stuff like that. But one of my points here is that it's difficult to say with a lot of these techniques that if I apply anonymization with this privacy parameter, I will not have information loss worse than this. I'll have a bound. And that's one of the limitations of the technique. They tend to kind of transform the data until some structural criterion is met, do a certain number of edge additions or deletions or cluster nodes together in groups of certain size. And for different data sets, that may result in very different levels of distortion for different analyses and stuff like that. Okay. So I'm going to move on to differential privacy. So the intuition behind differential privacy is that the output of a differentially private algorithm will be indistinguishable whether or not a specific sensitive fact is present in the database. So if you're worried about disclosing your sensitive fact, you have the assurance that the answers that the mechanism is providing will not reveal anything because they're statistically indistinguishable. So the idea here, imagine we have a query and we think about numerical queries, so like a counting query that's going to count the number of nodes with degree 3. And imagine for the moment that our sensitive fact is the edge between Dave and Ed. I'm just worried about protecting that edge, disclosing that edge. So I can imagine another data set where I remove that edge completely. Well, now my mechanism needs to give an answer to the same query for that data set, and the intuition or the basic idea behind differential privacy is that these two answers will be statistically indistinguishable. So in the first case, on this toy example graph, the true answer to the query is 0. And I add noise and I get some answer P. On this other data set, which is called a neighbor because it differs only by one edge, the true answer is 2. I add some random noise to that and I get the answer Q. So we want these to be indistinguishable outputs, and in that way we have a guarantee that we've protected the existence of this one edge. All right? In fact, we want the output to be indistinguishable across any addition or removal of an edge. So the formal definition is shown here. An algorithm that satisfies differential privacy has to be a randomized algorithm. And it provides epsilon differential privacy if, for all pairs of neighboring graphs that differ in one edge, and any set of outputs, the probability of getting the output S on one of the neighbors, that probability is close to getting that output on the other neighbor, which results from removing an edge. And it's close. What I mean by saying these probabilities are close, they're close by this factor e to the epsilon. Epsilon is a privacy parameter. It's usually a small number, like 0.1. If epsilon's 0.1, then we have e to the epsilon as about 1.1, and we've kind of bounded the difference in these probability distributions. If we lower epsilon, make that number smaller, we bring the probability distributions together, we require that they are closer, and we enforce stronger privacy. Okay, so that's a formal definition. I'll give you some examples. Well, actually, no, I'm going to talk about the mechanism. So that's a definition, that's a privacy notion that is persuasive because it allows this intuitive notion of opting out of the database. It should provide almost as good privacy, subject to the privacy parameters, as if you weren't in the database at all. And it doesn't make any assumptions about the power of the adversary or their background knowledge. So in addition to this definition, the original work also provided a construction which satisfies differential privacy. So a way of designing algorithms, a way of answering queries that satisfies differential privacy. So here's the basic idea. We compute the true answer, which is Q, evaluated on our data set or our graph, G, and we add a random sample from a special distribution. It's the Laplace distribution. It's a symmetric exponential distribution. Its mean of the Laplace is 0, so that the mean of the output is the true answer. But there's some variance around that output, which is controlled by this B parameter. So let me show you an example. When on the last slide, I had this sample query, number of nodes with degree 3. The true answer to the query was 0. So if I'm going to output an answer, I'm going to add random noise, and I'm going to draw a sample from that red line on the left. It's centered around 0, and it's got some variance, right? Now, if I am instead answering the same query over the neighboring data set, for which the true answer was 2, then I would be sampling an answer from that gray line. And the definition of differential privacy says that those distributions can't be too different. And I'm worried about the maximum difference. The maximum difference is indicated by that yellow line on those graphs. The probability of answering 2 on the first database is rather low. It's the red point. The probability of answering 2 on the other database is rather high. That's the difference. That needs to be bounded, subject to my privacy parameter epsilon. If that yellow line on the left is too big, it's bigger than I want it to be, that's a kind of policy decision about how big I should allow that to be, then I'll change the scale of the Laplace distribution. The Laplace 1 distribution will go to a Laplace 2 distribution. That means that the distribution's fatter, there's more error introduced, but that yellow maximum difference between the distributions has been reduced. And so we provide more privacy by increasing the scale of the Laplace distribution. In fact, what we need to scale the noise to is these two parameters. The privacy parameters in the denominator. So if it's a tenth, then we multiply the scale by 10. But in addition, we have this measure called the sensitivity of the query. The sensitivity of the query measures how much the answer to my query can change over neighboring databases. It's basically how much I might have to move the distributions. They might have to slide over neighboring databases. So I'll define that formally. The sensitivity of a query, it's a property of a query. It has nothing to do with the particular database, particular graph I'm looking at. It's a static property of the query, which is defined to be the maximum difference over any two neighboring graphs in the value of the query. Okay, so let me make this concrete. We've got a query like the degree that asks for the degree of a node A, some identified node. I say, what is its degree? Sensitivity of that query is 1. Why? If I add an edge to a graph, I change 2 degrees, each by 1. Well, one of them could be the node A, and that degree would go up by 1. But I could never add an edge and cause A's degree to go up by more than 1, or delete an edge and cause it to go down by more than 1. So the sensitivity is 1, and I would compute the true answer to that query, which is 4, and I'd add a random sample drawn from a Laplace distribution with scale 2. If I think about another type of query, a count query, which counts the number of nodes with degree I, some degree I, sensitivity of this query is actually 2. So if I add an edge to a graph, again, I change 2 degrees, each by 1. Well, in the worst case, I could have added an edge to 2 degree 5 nodes. Both of those nodes become degree 6. So how many nodes have degree 5 after I add that edge? 2 fewer, because 2 of them now have degree 6. So the sensitivity is 2, and then I add correspondingly more noise to that query answer. So I need to understand the sensitivity of the queries that I'm going to answer under differential privacy. Oftentimes that's not too hard, but it's something you have to prove. You have to think about it and prove this is the sensitivity, worst case change in my query answer over 2 neighboring databases. And then we know how to calibrate the noise for that query. So to a first approximation, what happens is that if we are interested in answering queries that have low sensitivity, then we can add low noise and get accurate answers out. If we want to try to answer high sensitivity queries, we have to add high noise, and we get noisy answers that aren't so useful. So there's one more wrinkle, actually 2 more wrinkles I have to tell you about. If I want to ask more than one query of a differentially private interface, I can do that. I can do it interactively, but I'm not going to really talk about interactive querying in this talk. Instead, I'm going to imagine that I bundle a bunch of queries together into a vector of imagine it's a vector valued query. It returns a list of numbers. If I do that, there's an easy way to extend what I had in the last slide to calculate the sensitivity and calibrate the noise. So here's how it works. If I ask a list of degree queries, the degrees of A, B, and C, and I bundle those together as one query, then I have to think about the sensitivity of that as a vector, which is the sort of sum of the absolute values in each component, the L1 distance for vectors. So if I ask for the degree of A, B, and C, the sensitivity goes up to 2, because if I add an edge, remember I changed the degree of 2 nodes, and I might have added the edge between A and B, and then A's degree goes up by 1 and B's degree goes up by 1. But I could never change more than 2 degrees by 1, so the sensitivity is 2. So I'll compute the true answer, which might be a vector 141, and then I add independent Laplace noise to each component. That's the slight extension of what was on the last slide. I can answer a set of queries this way. It turns out that the count query sensitivity goes up to 4, but it's independent of the length of that vector, so it's still a constant that's relatively low. Okay, the last wrinkle is that differential privacy, as I've described it, is it's calibrating the noise to protect the addition or deletion of edges to the graph, single edges. And I've given you enough examples, I think, earlier in the talk to point out that the sensitive information in a social network is not necessarily a single edge. It may be a node's degree or certain patterns of edges that exist that we may want to hide. So what we're working with is a notion that we call k-edge epsilon differential privacy. It requires that the algorithm output be indistinguishable whether or not any set of k-edges is added or removed from the graph. It's a simple extension to the one-edge case. You could argue that for privacy you would really like to have node epsilon differential privacy. That might be the firmest standard for security, but I think that is going to destroy a lot of properties of the graph. It's going to introduce too much noise, and k-edge differential privacy can do a pretty good job if you turn k up to numbers that approach the maximum degree in the graph. Okay, so ask me about that later if you want to talk a little bit more about that setup. Okay, so that was differential privacy. It's a technical definition. I had to go through the technical stuff to make our contributions understandable. All right, so now our task is study the degree distribution of a graph, the degree or the degree sequence. The degree sequence is the list of degrees that occur in a graph. Okay, so I look at every node in the graph. Each node has some degree, and I want to look at that list of degrees. It's a basic property that many people, sort of the first thing you look at when you want to understand what's going on with my graph. That is the degree sequence of our toy graph. When graphs are big, we'll look at the degree sequence as the inverse cumulative distribution, which is a graph which shows on the x-axis the different degrees of the graph. And for example, on the left-hand side, you have nearly 100% of the population has a degree greater than 0, and then it goes down to the right. Okay, so is the degree sequence itself really sensitive? Do I have to protect this? Let's take a moment to think about that. You might argue that the degree sequence itself is a kind of summary statistic about the graph, and maybe it's safe to just release exactly the degree sequence. Well, I would argue no, because for one reason, in extreme cases, the degree sequence of a graph could uniquely determine a graph up to isomorphism. So if every node happens to have degree k, then there is only one graph. And if you release that degree sequence, you will have done essentially the same thing as naive anonymization. You will have published an isomorphic copy of the graph. Now, that's unlikely to occur in real graphs, that everyone would have the same degree, or that the degree sequence that would uniquely determine a graph, but it's hard to reason about how many different graphs there might be conforming to a degree sequence. In addition, the degree sequence may not be the only statistics that we want to release about a graph. So we want to answer the degree sequence in this framework of differential privacy, and then we could also know how to answer other queries about graphs, and we would still have a sort of integrated privacy guarantee. Okay, so our basic task is estimate the degree sequence accurately under differential privacy. And here are two natural attempts, and they're based on the example queries I showed you when I was explaining differential privacy. We could ask for a vector of numbers, which is just the degree of every node. We have some way of indexing the node. We ask for the degree of each node. The sensitivity of this vector is 2, so I know how to calibrate noise, and the noise will be added will be independent in each component. I could also ask for a slightly different query, which is the frequency of each degree. Okay, that's also a vector of length n, but starting from 0 going to the maximum feasible degree of n minus 1, and it just counts how many individuals have that degree. That has sensitivity which is a little bit higher, but still relatively low, sensitivity of 4. So here's what I get if I apply those techniques and I try to estimate the degree sequence of the ORCID network, a sample network that we played around with. Both of these estimates, the blue line and the green line, are not very good estimates of the black line. I think you'll agree. So what's going on with the blue line, which is the set of F queries, which is the frequency of each degree. In a social network, what happens is that you've got, in ORCID has like on the order of a few million nodes. The maximum degree in most social networks is much lower than n. Because if you think about the social networks that you may participate in Facebook has 100 million users, but there aren't many people with degrees higher than a few thousand, okay? So if I sample counts of all the degrees, what I have is this enormous part of the sequence which is asking for how many people have degree 100 million and 100 million minus 1 and all of these. And the answer is 0 in all of these cases, but I'm adding random noise. Sometimes I get a negative number, and I could round that to 0, but sometimes I get a positive number, and then it looks like I have one person in my data set with degree 100 million. In fact, when there's so many of those observations that it looks like there's a lot of people with really high degrees. And that blue line that you see is measuring that. The percentage of the population with degree greater than 500 is still 100. Okay? Now, there's a different problem with the green line, which is the D query, which asks for each person's degree, and that is that there's a lot of common low degree nodes, and those sometimes get randomly perturbed beneath 0 and get rounded to 0, so there's a lot of zeros, and that's why the green line starts lower than 100%. Okay, so here's our innovation. It seems like a simple trick, but it turns out to be kind of a deeper technique. So instead of asking the D query, I'll compare it to the D query. We ask for the degree of each node. We actually don't care about the association between people and their degrees. We just want a multiset of the degrees that occur in the graph. So any permutation of those numbers is fine to return to us as an analyst. In fact, the permutation that we'll choose is the permutation which ranks the degrees. So I start with the lowest degree in the list and I go up to the highest degree. I'm going to add random noise to that query, but I'm going to ask for the query in ranked order. It turns out, and you have to think about this a little bit, and I won't prove it to you, but it's not too hard to see that the sensitivity, even if you sort the list, doesn't change. It's still the same sensitivity, which means the same noise will be added. But the advantage of asking for this ranked query is that I have a whole set of constraints that I know hold over the true answer. And when they're violated by my noisy output that I get, I can use that to my benefit. So let me show you how we use that. This is a toy example, and I'm displaying the degree sequence a little bit differently here. This example has a bunch of 10-degree nodes, and then a 14-degree node, and then a few 18-degree nodes. And they're displayed horizontally there by in order, and the degree on the y-axis. That's the true sequence is in black circles. The random output I get is going to add independent noise to each of those degrees. So instead of getting 10 across all those first degrees, I'm going to get the green dots, which are slightly higher than 10, slightly lower than 10. And then I'm going to get some other values. So this is a little strange because it violates the sort constraint. A sorted list is non-decreasing. It can be flat, but it can't go down, right? So what's strange about this is that the 19th element in my array should be the 19th smallest degree, but some noise has been added, and now it actually looks like the smallest degree. And I know that can't be right. So as an analyst, I can refine the green sequence and come up with a better estimate. The way I do that, the way we do that, there's more than one way to do that. The way we do that is we generate an inferred sequence, this red line, which minimizes, it's a non-decreasing sequence, so it satisfies that sort constraint. And it's the non-decreasing sequence that minimizes the distance between the observed values. You could minimize the L1 distance, but we happen to minimize the L2 distance because it gives us a unique answer, whereas the L1 distance doesn't. So, we take the noisy output that we get. We know that some constraints are supposed to hold. Those constraints are violated. So we refine the noisy output and we get a better estimate. That's the basic idea here. Here's what it looks like when we run experiments on, here it's some synthetic data. So the black dotted line is the true degree sequence, and the red line is, the green line is what we would have gotten with the standard technique. The red line, which is pretty close to the black line, is what we get from the inferred sequence. So it's a lot better, and the two cases here have different privacy settings, so there's more noise added in the case above. This, on the right, that's the same example data, and on the left are two new data sets, ORCID and LiveJournal. You can see that the red series is quite close. So what's going on here? It seems, when you first hear about this, like I've given you the noisy output that you told me I had to add this much noise to make it private. But then I've somehow inferred a better answer. So haven't I weakened the privacy? Is this a threat to the privacy guarantee? And it's not. So what I've done is I've formulated my query in a way that has constraints that hold. The constraints are a property of the query, though. They say nothing about the data. I submit the query to the differentially private interface, and I follow all the rules that were laid out for me by the differentially private mechanism. In fact, we kind of use differential privacy in only the standard way. All of our techniques are sort of post-processing the output. So we get the noisy output, which I'm writing here as S tilde, and then we perform our inference technique using no information from the database to infer S bar, which is the better sequence. So this is my argument for why it doesn't weaken privacy. The intuition is that the standard independent Laplace noise that we add using the construction that's classical for differential privacy adds more noise than is necessary. It's certainly sufficient for differential privacy, but no one has shown that it's necessary for differential privacy. And what these results show is that it's not necessary. It's more noise than we need. So by using inference, we're in some sense adding noise where the noise needs to be. The sorting trick, in some subtle way, capitalizes on the fact that the sorted sequence I'm asking for can only change in certain parts. So if I add an edge to a graph, remember that I change 2 degrees each by 1. But in the sorted list, if there's a bunch of 10-degree nodes, I can never change the fact that the 10th node in that list is 10. I could change the ones at the tail of that common sequence and at the end, and I could change these other ones, but I can't change those ones in the middle, so I can get away with adding less noise there. That's the intuition. I mean, making that, realizing that is tricky, because if you add a different noise distribution, you have to still prove that the differential privacy holds. So we tried to represent the noise that we add to the inferred sequence can be seen as some random sequence produced from the original input, but it seems very difficult to describe that probability distribution directly, and our inference step kind of gets around that. If you look empirically at how we add noise by running a bunch of experiments on a sequence like this, you'll see that the noise that we add, what we do is we run a bunch of experiments where we add the noise and then do the inference and get the better answer out, and then we look at how noisy that better answer is. And what it reflects is that noise is added where the sequence can change and not otherwise. Okay, so the theoretical bits are that we can also prove that our error is lower. So instead of having order n error for the S tilde sequence, we have error that's polylogarithmic in n, which is good, and there's a factor d, which is determined exactly by what I was saying, the length of sequences of common degree. The longer those sequences of common degree, the better the trick works, the sorting trick works, and error is reduced. The thing that's great about degree sequences of social networks is they have lots of common degrees, especially in the earlier regions. So in practice, we get a big boost from this technique. The algorithm's also efficient, so finding that red line, minimizing the L2 distance, is a little tricky. I mean, it's worth asking whether you can do that efficiently. You can't always apply such constraints efficiently, but in this case we can. And we've got that running in recent work in linear time in the sequence. So we could actually run this algorithm on massive graphs. Okay, I'm getting close to running out of time, so I'm going to skip the 2 slides I have on privately counting motifs. The main idea here, motif analysis is basically studying the frequency of occurrence of small patterns in a social network. So a classic example is transitivity. How often if I'm friends with A and I'm friends with B, are A and B friends, and how likely does that occur? But in general, you might want to study other patterns that you think are interesting, or you might want to search for patterns that occur more often than you expect them to occur, things like that. Counting motifs is a fundamentally harder analysis to do under differential privacy. It's higher sensitivity. In fact, its sensitivity is very high, so much so that standard differential techniques are probably going to return useless answers. So we have a technique which weakened the privacy notion a little bit and improves the error. So I'm going to skip over this and talk briefly about where we're headed with this work. So I mentioned in the beginning that data publication is great for ease of use because you can hand somebody a graph and they can study it. We're using output perturbation, so we're considering specific tasks, breaking them into a bunch of queries, and learning how to, if we can answer those queries accurately. So I think that's the first step in a process which we hope will result in techniques for data publishing. So I'd like to still hand the analyst a graph, but I'd like it to be a synthetic graph that I've derived through a differentially private process. Our best attempt at that, or we think our best chance at doing that, is learning the parameters of some model of the topology of a graph. Noise will be added to those model parameters, but then I'll publish the model parameters. I don't have to just publish a sample. If I learn the model parameters privately, I'll just publish the model. And then the analyst can generate as many sample graphs as they want, study them. There will be error in that analysis, and we'll have to measure that, and we'll have to relate that to the error in the model parameters. But that's kind of where we're headed. We think maybe we'll get the best of both worlds from that technique. Okay, so I'm going to skip this. The last thing I'll mention is that this paradigm for using the standard differentially private construction, but capitalizing on constraints to improve accuracy, we've used this for other stuff. So not just the degree sequence, but other histogram queries. And we've shown that it can improve accuracy for other tasks. And we think that it's a promising technique that has some more generality. So that's a paper that's going to appear in PVLDB next year. I'll end with that and invite any questions. Thanks for your attention. Yeah, hi.
So I have two questions actually. The first one is, this whole literature assumes fairly static audience who is not actively aware of the publication of data and therefore doesn't change their behavior accordingly. But hypothesize that maybe the participants in the network are, at least some of them, are privacy sensitive. And so they are told ahead of time that what gets published is the anonymized, naively anonymized. They could presumably change and create links to hide in a bigger crowd, so to speak. Become less distinguishable.
Yeah.
Can you speculate on this ability to hide in a crowd, by modify your behavior to hide in a crowd? Is this impaired or enhanced, or it doesn't matter by the extra techniques that you use of noise injection and all of that? What effect would it have?
Well, let's see. So I can speculate on anything because it's speculation, right?
That's already we can ask.
Right. So, so I think with our techniques, it would be very difficult to mount a re-identification attack based on structure. I mean, so we're not publishing a graph right now. We're just publishing a degree distribution right now. But if we carry forth the work and publish synthetic networks, those should be, if I'm satisfying K epsilon differential privacy, then I'm publishing results that are insensitive to any addition or deletion of up to K edges. So that's one point to make. I mean, the other point is that, I guess a lot of the anonymization techniques are trying to distort the graph to create structural similarity. I guess what you're pointing out is that you could do this as a participant in the network.
Self-defense.
Yeah, as a means of self-defense. And
no matter what you publish, I'm not assuming naive. It could be degree sequence.
Yeah,
Be suitably modified.
Yeah, I think that I think that we'd like to be able to guarantee that a user that's not necessary. And I think it's not necessary if there's this wrinkle here about K edge differential privacy. So the fact is that if for a fixed K, I'm offering a different protection to low degree nodes than I'm offering to high degree nodes, because the degree of low degree node should be completely sort of obscured by under K edge differential privacy. And this is a bit of a departure from the standard setting, but I don't see a way around it. So I still think that, actually we did some experiments which show that the maximum degree in a graph is so low that you can turn that K parameter up to nearly the maximum degree and still get accurate degree sequences out, which is somewhat surprising. So you can get almost node level protection even for the highest degrees. At some point you have to argue about whether it's reasonable to try to protect outliers. hubs, you know, the very highest degree nodes in a graph, some people can argue sort of everyone knows who they are. I mean, maybe a significant percentage of the people connect to them in the population. So how can they be hidden? And so you can make, these are more sociological arguments about what privacy standards are okay in the population, but I don't know. So I've speculated broadly in response to your question. Sorry if I didn't answer it. So did you have another question? Or?
Well, I was going to ask you also whether there's any literature over that takes snapshots over time and it makes inferences based on that.
Yeah.
For example, that you could have someone who is so wildly difficult that from one snapshot to the next, they've lost so many friends that you say, oh, this has got to be Joe right there.
Right, right. Yeah, there are subtleties there.
Such literature,
Yeah, in fact, some of your collaborators here at Purdue have done some initial work in the framework of k-anonymity on these sequential releases of data, and there are subtleties there. I think the differentially private model is robust to some formulations of problems like that. So I mean, if you're worried about a single edges, I mean, you can let your database evolve and continue to ask questions, and noise is added, and it should protect edges, even edges that are changing. I mean, of course, you run into the problems that your privacy budget gets exhausted potentially under differential privacy. So eventually, you have to stop asking questions where the noise keeps increasing. Yeah. Any other questions?